Planetary habitability is the study of which worlds can support life, and of how astronomers might recognize that life from across the immense gulfs of space. Astrobiology converges on three minimum requirements for life as we know it: liquid water to serve as a solvent, a usable source of energy, whether sunlight or chemical gradients, and the essential elements assembled into organic chemistry. A habitable world, then, is one that can maintain liquid water in contact with an energy source, and those elements. The emphasis on water is physical, not merely parochial. Water is an exceptional solvent that dissolves and carries the ingredients of metabolism. It stays liquid across a wide range of temperatures. It has an unusually high heat capacity that buffers a planet's climate through evaporation and condensation. And strangely, it is less dense as ice than as liquid, so that ice floats and insulates the water beneath rather than freezing a sea solid from the bottom up. Life as we know it is built from a small set of light elements: carbon, hydrogen, nitrogen, oxygen, phosphorus and sulfur, exploiting carbon's fourfold bonding to form the long, stable yet reactive molecular chains that store information and metabolism. Alternative chemistries are studied as a hedge against our terrestrial bias: ammonia or liquid methane as solvents, silicon in place of carbon, but each faces real handicaps, so water and carbon remain the conservative, testable baseline. Water's own phase behavior then sets hard limits. Below a certain pressure, the pressure of its triple point, no liquid water is stable at any temperature, and ice simply sublimates straight to vapor. This is why present-day Mars, whose thin air sits almost exactly at that pressure, can host only fleeting films or salty brines rather than standing seas. Habitability requires both a temperature in the liquid window and an atmosphere thick enough to keep that water from boiling away into the vacuum. These constraints motivate two ideas that run through the whole subject. Surface habitability concerns liquid water exposed at the surface and lit by the star, the kind relevant both to photosynthesis and to sensing from afar. Subsurface habitability concerns water kept liquid by a world's own internal heat, deep beneath a shell of ice or rock, and wholly cut off from starlight, as on Jupiter's moon Europa or Saturn's Enceladus. The circumstellar habitable zone, the organising concept of this chapter, formalises only the first of these. That is precisely why it is necessary but not a sufficient guide. It marks out where a suitable planet could have surface water, not whether any particular planet there actually does, let alone whether it is inhabited. The circumstellar habitable zone is the range of orbital distances over which a rocky planet with an Earth-like atmosphere could sustain liquid water on its surface, as worked out from detailed climate models. The foundational calculation dates to work by James Casting and colleagues in the early 1990s, refined into the modern standard by Koparapu and colleagues 2 decades later. The inner edge is set by the loss of surface water through two related runaway processes. In the moist greenhouse, a rising surface temperature drives water high into the atmosphere, where sunlight splits it apart and the hydrogen escapes to space, slowly desiccating the planet. In the full runaway greenhouse, the absorbed sunlight simply exceeds the heat the atmosphere can radiate away, the oceans evaporate entirely, and the surface roasts, the fate that befell Venus. The outer edge is the maximum greenhouse limit. As a planet is placed farther out, one can add carbon dioxide to trap the dimmer starlight, but beyond a point the gas scatters and condenses faster than it warms, and no amount of it can keep the surface above freezing. For our own Sun, these edges fall roughly between the Earth's orbit and about 1 7/10 times that distance, with the Earth sitting comfortably inside. A more optimistic zone is bracketed instead by two empirical markers: a recent Venus inner limit, since Venus has had no liquid water for at least 1 billion years, and an early Mars outer limit, since Mars plainly had surface water long ago when the Sun was fainter. Beneath all of it lies a simple energy balance. Equate the sunlight a planet absorbs to the heat it radiates, and you get its effective temperature, which for the Earth comes out around 255 Kelvin, well below freezing. The 33-degree gap up to Earth's actual life-friendly surface temperature is the greenhouse effect, and the habitable zone is essentially the question of where the combination of starlight and a self-consistent greenhouse holds a surface in the liquid water window. Two caveats are essential and often forgotten. First, these boundaries come from one-dimensional, globally averaged cloud-free models of an Earth twin, and clouds, spin rate, atmospheric mass and composition all shift the edges considerably. Three-dimensional models show the simple limits are best treated as fuzzy reference lines rather than hard walls, and for a slowly rotating planet, a thick deck of cloud on the sunward face can raise its reflectivity and push the inner edge inward. Second, the zone is a statement about the potential for surface water given a suitable atmosphere, not a guarantee of anything. A planet can sit squarely inside it and still be a bone-dry, airless, or runaway world, for Venus itself lies near the inner edge of the optimistic zone. The familiar headline that equates any habitable zone planet with an Earth-like or habitable world claims far more than the concept can deliver. The host star controls where the zone lies, how wide it is, and how long it lasts. Because a star's brightness climbs steeply with its mass, the habitable zone of a hot, massive star lies far out and is broad, while that of a cool red dwarf is squeezed into a small fraction of the Earth-Sun distance. The color of the light matters too, for red dwarfs pour out most of their energy in the near-infrared, which water and carbon dioxide absorb efficiently, modestly widening the zone. And no star holds a fixed brightness. Main sequence stars slowly brighten as they age, so that our own sun was only about 70% as luminous 4 billion years ago, a puzzle known as the faint young sun. The zone therefore migrates outward over a star's life, and the continuously habitable zone, the narrower band that stays habitable long enough for life to evolve, is narrower still. Stellar mass cuts both ways. Massive stars are short-lived, a hot star burning out in a few 100 million years, plausibly too brief for complex life to arise, whereas red dwarfs shine steadily for far longer than the present age of the universe, offering almost unlimited time. Against that stability stands stellar violence. Low-mass stars are magnetically turbulent, firing off frequent flares and blasts of high-energy ultraviolet and X-ray radiation, especially during a long and luminous youth. This radiation heats the top of a planet's atmosphere and drives it to escape into space, and because hydrogen is the lightest atom, it is lost most easily of all, so that the steady leakage of hydrogen from sunlight-shattered water can dry a planet out entirely over time. Venus preserves a record of exactly this. Having lost whatever early ocean it had to a runaway greenhouse, its atmosphere now shows a ratio of heavy hydrogen to ordinary hydrogen about 150 times the Earth's. The explanation is escape sorted by mass. Ordinary hydrogen slips away more readily than the heavier form, so the water left behind grows steadily enriched in the heavy kind, a chemical fingerprint that a great reservoir of water was boiled off and lost. The same reasoning applied to distant worlds is one proposed way to test whether a hot planet has suffered its own catastrophic drying. Concern about such loss is not abstract. The very nearest star, Proxima Centauri, is a flare star observed to unleash enormous superflares, casting real doubt on whether the small planet in its habitable zone could hold onto a gentle atmosphere at all. A planet inside the habitable zone is only potentially habitable. Whether it truly is depends on its own properties, beginning with mass and make-up. A world must be heavy enough to grip an atmosphere against escape, to sustain long-lived volcanism, and to keep its interior hot enough for tectonics and a magnetic dynamo, yet not so heavy that it gathers a thick blanket of hydrogen and helium and becomes a small Neptune rather than a rocky world. This very divide is written into the exoplanet population, whose sizes cluster into two groups split by a scarcity near 1 4/5 the Earth's radius. The smaller worlds are rocky super-Earths, the larger ones gas-shrouded sub-Neptunes, and the gap between is thought to be carved by atmospheric escape stripping the envelopes from the smaller, more strongly irradiated planets. For surface habitability, one wants the rocky worlds below that gap, wearing thin secondary atmospheres rather than a primordial hydrogen sky. Long-term climate stability is widely credited to a slow geological feedback called the carbonate-silicate cycle. Carbon dioxide dissolves in rain and weathers silicate rock. The products wash into the sea and are laid down as carbonate. The grinding of tectonic plates carries that carbon down into the interior, and volcanoes breathe it back out. The feedback is self-correcting. A warmer, wetter planet weathers faster and draws the gas down, cooling itself, while a colder planet weathers slower and lets volcanic gas build up and warm it. This planetary thermostat is thought to have held Earth's surface temperate against the 30% brightening of the sun across its history, and it is what gives the outer edge of the habitable zone its physical meaning. Whether the cycle strictly needs plate tectonics, or can run on a one-plate, stagnant-lid world, is an open question that bears directly on how common lasting habitability really is. Other proposed ingredients are more debated. A planetary magnetic field, generated by a churning molten core, is often invoked as a shield that holds off the stellar wind, but its necessity is genuinely uncertain since Venus keeps a crushing atmosphere with no such field, while Mars's loss of its own field is widely blamed for the thinning of its air. The fair summary is that a magnetic shield probably helps in some cases, but is neither clearly required nor sufficient. Two more dynamical factors matter. The Earth's gentle axial tilt is held steady against wild, chaotic swings by the gravity of its unusually large moon, and the slow Milankovitch wobbles in tilt and orbit already pace the ice ages. And a world's endowment of water must be just right, for too little leaves a desert, and too much may drown every last scrap of land and switch off the weathering thermostat. Not one of these is captured by orbital distance alone, because roughly 3/4 of the galaxy's stars are red dwarfs, and many are found to host small planets. Red dwarf systems dominate the roster of nearby, reachable habitable zone worlds, and they are the only systems where an Earth-sized planet's atmosphere is within reach of transit spectroscopy in the near future, since the small star yields a deep and frequent transit, yet their habitability is fiercely contested. The central complication is tidal locking. A planet orbiting close in the zone of a red dwarf is braked by tides into synchronous rotation, so that one face is held permanently toward the star. The early fear was that the dark hemisphere would grow cold enough to freeze the whole atmosphere out onto its night side, but three-dimensional climate models have since shown that a thick enough atmosphere, or an ocean, can ferry heat around to the night side and prevent that collapse, so a locked rotation does not, by itself, rule habitability out. The deeper worry is the star's ferocious youth. A red dwarf spends hundreds of millions of years in a bright pre-main sequence phase, during which a planet now sitting in the habitable zone would have been scorched, quite possibly losing its water to an early runaway greenhouse and to radiation-driven escape before the star ever settled down, with persistent flares eroding the air thereafter. The net effect is captured by the idea of a cosmic shoreline, a dividing line, across which whether a world keeps its atmosphere depends on the contest between its gravity and the total high-energy radiation it has absorbed. High-gravity, gently lit worlds keep their air, while low-gravity, heavily bombarded ones lose it. Close in red dwarf, planets sit on the wrong side of that line unless they were born massive or especially water-rich. Whether they are oases or sterilized rocks is exactly the question that measuring their atmospheres, rather than arguing, is meant to settle. The circumstellar zone speaks only of surface water warmed by starlight, yet the solar system's greatest reserves of liquid water lie far outside it, in hidden oceans beneath the ice of frozen moons, kept liquid by the heat of tides rather than the light of the sun. Jupiter's moon Europa conceals a global salt ocean under its crust, plausibly holding twice the water of all Earth's seas, warmed as the moon is flexed by Jupiter's gravity. Saturn's little moon, Enceladus, offers the most direct evidence of all. The Cassini spacecraft flew straight through plumes jetting from cracks at its south pole and tasted water, salts, molecular hydrogen, methane, and complex organic molecules. That hydrogen is most easily explained by ongoing chemical reactions between the ocean and a rocky seafloor below, the very same reactions that feed thriving communities of life around the deep-sea vents of Earth, and a possible energy source for life quite independent of any sun. These discoveries reframe the entire search. For a subsurface ocean meets the same three requirements as any habitat, and crucially its energy need not be sunlight at all, since the chemistry at a rocky seafloor can power life in total darkness, exactly as it does at Earth's mid-ocean vents. An external habitable zone is thus not required for this kind of world, and ocean moons may be the single commonest habitable environment in the cosmos, simply because icy moons are so abundant. Titan extends the catalogue further still, the only other body with stable liquid on its surface, though those are lakes of methane and ethane rather than water, wrapped in a thick atmosphere and a rich organic chemistry, and probably hiding a deep water-ammonia ocean of its own. The great drawback of all these buried habitats is that a biosphere sealed under kilometers of ice sends no signal we could read from light years away, so studying it demands going there, which is why NASA Europa Clipper, launched in 2024, will make dozens of close passes to probe Europa's ocean directly. For worlds too distant to visit, we must read life if it is there in starlight, and this is the science of biosignatures. A biosignature is some observable feature, a gas, a color, a rhythm that is better explained by life than by any known lifeless process, sort in the light that filters through a planet's atmosphere as it crosses its star, or in the light it reflects. Such signatures fall into three kinds: gases made by metabolism, surface features of living material, and changes over time driven by a biosphere. The classic gaseous candidates are molecular oxygen and the ozone it forms, kept abundant on Earth only by photosynthesis, together with methane, richly produced by life, and nitrous oxide, almost wholly biological. But the single most robust clue is chemical disequilibrium, the simultaneous presence of gases that ought to react away with one another, such as oxygen and methane, which coexist on Earth far out of balance, and so must be constantly resupplied by living things, a combination very hard to fake without a biosphere. Surface and temporal signs round out the picture. The best studied surface feature is the vegetation red edge, the sharp rise in brightness with which land plants reflect light just beyond the red. Though averaged over a whole cloudy, ocean-covered disk, it amounts to only a few %, a demanding target. Temporal signs include the seasonal breathing of carbon dioxide as vegetation grows and dies back through the year. But every biosignature is haunted by the false positive, some lifeless process that mimics the mark of life, and careful modeling has shown that oxygen and ozone can in fact build up without any biology, for instance from sunlight splitting water on a drying world, or from carbon dioxide chemistry around active red dwarfs. There are false negatives too in habited worlds, like the early Earth. Before oxygen rose, that would leave no easy mark at all. The only sound response is to demand context, weighing a candidate gas against the star's light, the planet's history, and the whole of its atmosphere, rather than treating any one molecule as a verdict. The contested case of the planet K2-18b makes the stakes vivid. This sub-Neptune in the habitable zone of a red dwarf shows clear detections, by the Webb telescope, of methane and carbon dioxide, consistent with a hydrogen-rich, possibly ocean-bearing world. In recent years, a Cambridge-led team reported a faint, tentative signal of dimethyl sulfide, a gas made on Earth mainly by ocean plankton, and put it forward as a possible sign of life. But independent reanalyses confirmed the methane at high confidence while finding no statistically solid evidence for the dimethyl sulfide, and lifeless sources of that gas are entirely plausible, so the episode is best read not as evidence of life, but as a sharp lesson in how marginal a frontier biosignature really is. Extraordinary claims will demand reproducible, high-confidence signals, and the firm elimination of every lifeless explanation. The search itself runs on two tracks, counting how common potentially habitable planets are and characterizing individual worlds in detail. The running tally of confirmed exoplanets now stands at around 6,000, found chiefly by the transit method and the stellar wobble, of which only a small fraction are rocky worlds in their stars' habitable zones. From the transit surveys, astronomers also estimate how many Earth-sized habitable zone planets there are per star, a number that directly sets how large a future telescope must be, and one that is genuinely uncertain, since it means extrapolating incomplete data down to the smallest and most distant planets. The best estimates run to roughly one such world for every few Sun-like stars, but with wide error bars. The TRAPPIST-1 system, 7 Earth-sized planets around a nearby cool dwarf with several in the optimistic zone, is the prime natural laboratory, and Webb has already ruled out thick atmospheres on its hot inner planets, while the spectra of its habitable zone world remain confused by the contaminating flicker of the star itself, not yet settling the question. Deciding the case for an Earth twin around a Sun-like star will require seeing the planet directly, since such a world neither transits reliably nor shows a readable atmosphere in transit, and this is the mandate of the proposed Habitable Worlds Observatory, recommended as the great flagship of the 2040s. Its defining goal is to image and take the spectra of around 25 potentially Earth-like planets in the habitable zones of nearby stars, and to search them for oxygen, ozone, water, and methane. The enabling feat is to suppress the glare of a star by a factor of 10 billion, so as to reveal a planet a few tenths of the Earth-Sun distance away from a star 10 billion times brighter, a technology the Roman telescope's starlight-blocking instrument will begin to demonstrate. It remains a mission still being designed, and any hint of life it might return would face all the false positive scrutiny already described. Habitability, finally, has a galactic dimension. The galactic habitable zone is the notion that only part of the Milky Way is hospitable, a region enriched enough in heavy elements to build rocky planets at all, yet not so close to, the crowded, supernova-riddled core that young biospheres are repeatedly sterilized. It is a model-dependent and much-debated idea, but a useful reminder that a planet's place within its galaxy and the slow chemical enrichment of the cosmos constrain where life can arise. The overall frequency of life is famously framed by the Drake equation, which multiplies together a chain of factors to estimate the number of communicating civilizations, the astronomical terms of which we can now measure, while the biological ones remain almost wholly unknown, so that the answers span many orders of magnitude. Against the easy assumption of abundant life stands the Fermi paradox, the sheer absence of any solid evidence for it despite the galaxy's vast age and size. And beneath every estimate lies the unsolved riddle of how life begins, for we have exactly one example and cannot yet say whether the leap from chemistry to living, evolving matter is all but inevitable on any gentle world, or a fluke of vanishing rarity. The rare Earth view holds that simple microbial life may be common, but the precise combination that allows complex life, a steadying moon, plate tectonics, a sheltering giant planet, the right galactic address exceedingly rare, the opposing intuition, drawn from how swiftly life appears in Earth's own record, holds that it springs up wherever it can. Neither can yet be tested, and so the habitable zone is best understood not as a verdict, but as a map of where to look first, with the real answers to come from the patient study of individual atmospheres, the exploration of our own ocean worlds, and in the end the detection, or the telling silence, of a living world beyond the Earth.